Hi everyone. Today we will continue discussing together the topics of the induction motor. We had 3 sessions before. This is the 4th session in the induction motor. So in the last session, we stopped at this slide here. So let me quickly remind you what we have discussed so far. In the first 2 sessions, we discussed the motor operation and we drive the equivalent circuit. Then in the third session, last one, we started discussing the approximated equivalent circuit, and we discussed the different circuits that we have, and we said we are going to continue with the approximated equivalent circuit in our classes. Then we derived the torque speed characteristic of the induction motor, and we understood the concept of what are the operating regions here, the stable region and the unstable region. And we discussed or simplified the meaning of stability. And then we derived some relations that are important to be used to solve the problems. Just to remind you, what are the objectives again? The objectives are to drive the induction motor characteristic, learn the performance of the induction machine, drive the maximum torque, learn the different modes of operation. So for the time being, we finish some of these objectives and we continue the remaining objectives during our session today. So let's see, guys, the features of the starting point. So starting point, and this is very important to understand the dynamic equation of the induction machine. And the dynamic equation, guys, is not only for induction machine, it's for any electromechanical device. Okay, so it's very important to figure out the meaning of the dynamic equation and how this affects the operation and stability of any device. Okay, so let's start, guys, with the approximated equivalent circuit again. So if you would like to get a starting torque, mathematically from our relations here, you can find that S in our relation here at starting, it should be 1. So if you apply the mathematical model at S equals 1 and get the current, for sure, since S is very small, guys, we expect S to be like 0.02, 0.03, something like that during operation, okay? But at starting, it's 1. So if S is very small, this means the resistance R2 prime divide S is going to be very high, okay? And having this resistance very high, this will allow small current to flow in the circuit. This is for the small slip. But if S is very small, sorry, if S is very high or close to unity or unity at startup, in this case, the value of R2 prime divide S is going to be small, which is typically the value of the resistance of our rotor circuits. So in this case, guys, we expect to have more current flowing in the circuits. And this is the feature of starting of the induction motor. We will solve some problems, guys, and we will see that the starting current of the induction motor, so I at starting, is 5 to 7 times of I rated. So starting current, so if you have a motor, for instance, of 100 ampere, you can expect that the starting current can be from 500 to 700 amperes. It's very huge value, okay? Why? Because at starting S equals 1, this is mathematically and physically is at starting, you need to move the inertia of the motor. The inertia of the motor is the mass of your rotor. So this is going to be huge mass to be moved. So this is going to take very high energy in the starting. Once you rotate this mass, this big mass for inertia. So you don't need any high power anymore to run your motor. For that, the starting current of the induction motor is very high. Let's go back again to the equations. So if you apply at S equals 1 here, you will find that the torque at starting is, this is the regular torque equation, 3v square r2 prime divide r1 plus r2 prime divide s all square plus x equivalent square all times s times omega s. If you apply s equals 1 here in this equation, you will find that the value of r2 prime plus r1 is going to be very small compared to if s is small value. So we can say we may neglect this part compared to that part. Why we do such approximation, guys? To make the calculation easier for you. So if we neglect the part of r1 plus r2 prime divide s compared to x equivalent because s equals 1, so we can say our relation now is going to be 3v square r divide x squared times s omega s, but s equals 1, so it will be also removed from the equation. So we will end up with this equation for the torque starting. So this is the approximated equation for T starting. So 3v square r2 prime divide x equivalent square omega s. So this is the value of torque at starting. Value of torque at starting, guys, compared to the rated torque, it could be from 1 to 1.5. So for instance, here we have a certain operating point P. As you can see, TS is a bit higher than TP. Okay, so this is the feature of the starting of the induction motor. Torque starting is going to be like in a range from 1 to 1.5 of rated torque, and I starting, it will be from 5 to 7 from the rated current. Okay, nice. Now, let's move our discussion to the dynamic equation, and this is very important point, guys, we need to discuss. So, as we can see, the constant load torque needs a starting torque higher than the load torque. For any motor, guys, if you would like to start a certain load, the energy of the machine has to provide a torque higher than this torque. Otherwise, you cannot operate the motor. Why? So firstly, from the physical point of view, this makes sense because you cannot carry a load with a weight that is higher than your weight. If you don't have energy enough to carry a load, you cannot do that. So the same is for our motor. If our electrical torque is less than the load torque, so how the machine can operate this load? It's impossible. So this is from the physics. Let's see that from the dynamic equation point of view here, what is happening. The dynamic equation says T electric minus T load equals J d omega by dt. J is the moment of inertia. D omega by dt is the rate of change of speed, plus B times omega. B is the friction coefficient, and omega is the motor speed. So I do believe we discussed this equation before, guys, if you remember, in the closed loop control and modeling of the DC motor. So we discussed the dynamic equation of the DC motor, and we made the mechanical model and the transfer function of the DC motor. So we discussed this before for the DC motor, but let's understand the concept here for the motor starting using the dynamic equation. So B is the friction. If we neglect the friction for the time being, so omit this part from the equation. I'm going to say neglect the friction. So, and this actually is the case if you start a motor. So friction means you have a motor, this motor is working, and the shaft of the motor itself is rotating and has some friction with the bearings. But if the motor is not working, it's still at standstill, it's not started yet. So there is no friction. So we can say remove the part of this equation at starting. So if T electric minus T load is positive value, this means d omega by dt is going to be positive. And if d omega by dt is positive, this means the motor is going to be speeding up. And since the motor is still at zero speed, this means the motor is going to move. So d omega by dt is positive means the rate of change of speed is going to be positive, and this means if you are at zero speed, so the speed is going to be in positive, which means the motor is going to start. If T electric equals T load, so this means this term equals zero, which means the rate of change of speed is going to be zero. So if omega 1 is zero, which is the standstill, so this means the second case is going to be zero as well. I'm comparing like if I have like 2 points, 0.1 and 0.2, and getting the d omega by dt between them. So I have omega 1 and omega 2, and I would like to get d omega by dt. So again, if omega 1 is the standstill, so this is equal to 0. So I can say d omega by dt, if it is positive, so this means omega 2 is greater than omega 1, which has a value, so this means the motor is going to start. But if d omega by dt equals 0, so this means omega 1 equals omega 2. And this will not start the motor. And on the opposite side, if T electric is less than T load, so d omega by dt is going to be negative, which means theoretically omega 2 is in minus sign. So practically, this means it's impossible to start the motor because there is nothing called negative speed if the motor is stop or in standstill. So this will not start the motor. But it's even, guys, more worse, because if you apply the motor supply with the motor having electrical torque less than the load torque, the motor will try to absorb more current from the supply in order to make the torque higher. So it's like if you have a heavy load, very heavy load, you try to carry this load from the beginning, but you could not. So you do your best in order to move this load. So you will like consume more energy in order to carry this load. So this is the same physical meaning for the motor. So the motor is going to absorb more current from the supply in order to carry this heavy load, which means it will absorb more current in order to increase the electrical torque to move higher than the load torque in order to carry the load and start the motor operation. Okay, so this is the meaning of the starting torque. So we got the concept now. Starting torque has to be higher than the load torque in order to start the motor. Okay, and for any motor, guys, start from scratch, the torque will start from 0. So here we have Ts equals value, but this is actually not the instantaneous torque. This is the average torque. But the real characteristic of the motor is, I mean, not the real characteristic, I mean the torque with time, okay? The torque is going to be start from zero time from zero value. At zero time, or at the starting point, it will start from zero value and absorb current and increase. So let me show you that in another slide, just to imagine with me, guys, the how things are moving in reality. So if this is torque and this is time, so what will happen is the torque will start from zero, increasing and decreasing, increasing and decreasing, and so on until starting our load. So the average of this is going to be your starting torque. Okay, so you can find that in any uh, graduate book, not undergrad book. Okay, so this is a bit advanced. Okay, in order to see how the motor characteristic. Also, if you Google it, guys, you can find that clear here in Google. Torque speed curve of induction motor. Let me have some images to see if the exact curve is here or not. No, the exact curve is not here. Let's say instead of torque speed, torque time. Okay, it's not. Yes, we have something close to reality here. Okay, let me show you that one. So can you see here, guys? The torque here is the green one. Can you see the torque is oscillating until being stable? And now we can say the average is going to be like that. So this is the average. So the red one is the average. So we can consider that the value here is the starting torque, for instance. Okay, guys, so this is a real representation of the torque versus time. Okay, uh, I can share with you some of advanced publications for the induction motor operation, guys. Okay, so this includes more detail about the performance or the exact performance, including transient of the induction motor. But for the time being, again, let's return back to the steady state model. Okay, and we can assume that this is our torque value at starting. But again, theoretically or even practically, it should be starting from zero. But this is here the average value, not the instantaneous value of our torque. Okay, nice. I don't like to discuss with you for the time being, guys, the point of stability with the dynamic equation, but I'm gonna discuss that with you when we start discussing the speed control of the induction motor. Okay, so we'll go more in deep with the dynamic equation and how this part of the curve is unstable and this part of the curve is stable. Okay, nice. Okay, now let's start solving some numerical problems, guys, to sense the machine performance and evaluate the performance at different operating points. So this example, guys, is from the textbook we are working from, but the textbook is solving using the IEEE equivalent circuit and Thevenin analysis. What we are going to do in our class, we are going to follow the approximated equivalent circuit solution. And after solving the equations or getting the numbers, you can compare that with the values you have in the textbook. Okay, so we have here three-phase 460 volt, 1740 RPM, 60 hertz, 4 poles, wound rotor induction motor. So again, guys, for any question, you need to understand the words between lines. Every expression has a meaning. Every word in this code or the nameplate has a meaning. So you have to understand this correctly. 460 volt, this is line to line volt. So what is the phase value? I don't know. I need to check the connection. So from the code here, we said that it's wound rotor. I don't know yet. 60 hertz, 1740. Nothing says the motor connection. Since we don't have anything about the motor connection, you can assume that the machine is connected as Y. So we can say, assume Y connection. So we can say V phase equals V line divided root 3. This is with the assumption of we have Y connection. 1740 RPM. What is the 1740 RPM? You know that 1740 is impossible to be a synchronous speed because synchronous speed has definite numbers. Frequencies of our systems in the world, either 50 hertz or 60 hertz. And number of poles are going to be 2 poles, 4 poles, 6 poles, and so on. So if you apply the relation of 120F divided number of poles, you would find that this is here 3000 RPM, this is here 3600, this is here 1500, this is 1800. So it's definite numbers. We don't have like a lot of varieties of numbers for the synchronous speed. So definitely this speed means here it's the rotor speed, not the synchronous speed. But again, which operating speed? So if you read the nameplate data of any motor, guys, the speed is given for the rated speed. This is for the induction motor. The speed is given for the rated speed. DC motor was different. DC motor was the no load speed. Okay, so for induction motor, the speed given is the rated machine speed. The rated machine speed means if you apply the rated torque to this machine, the machine will absorb the rated current and run at 1740 RPM. So 1740 RPM means this is in rate or in full load. 1740 RPM. 60 hertz, this is our grid frequency. 4 poles, it has to be 4 poles because you know that 1740 RPM, this is the motor speed. It has to be very close to the synchronous speed, which is 1800 in this case. And 1800, it has to be 4 poles. This means, guys, in some questions, this number may not be given if you have this speed, because you can figure out that number of poles here has to be 4. It's impossible to be 2. It's impossible to be 6 because this is rated speed. Again, in case of 2, the synchronous speed is 3600. The machine can work at 1740 RPM, but this is very low speed, which means we have very high torque, so it's not rated. So the rated speed has to be close enough to the synchronous speed. And it's impossible to be 6 for sure, because 6 poles, we will have 1200 RPM synchronous speed. So the induction motor speed has to be less than the synchronous speed in motoring operation. Does it mean it's possible to have induction machine speed higher than the synchronous speed? Yes, this is correct, but in generator operation. Okay, and we will delay the discussion of this part when we discuss the modes of operation of the induction machine. So again, this is now the rated speed of our machine. Frequency is 60 hertz, 4 poles. Wound rotor. Wound rotor is the slip ring motor. So slip ring motor is used mainly for adding resistance and speed control using adding resistance. And by the way, guys, in industry, you may find such motors are used, but with very high power, like for instance, 500 horsepower motors, okay, for very high power machines. But for small rating machines, we do prefer to use the squirrel cage type. So the motor here had the following parameters per phase. R1, so R1 is the stator resistance. R2 prime is the rotor resistance referred to stator side. And all the time, guys, in the equation, in the questions, the parameters are gonna be referred. So it's not like transformer. You have to refer the values. So every parameter is gonna be given already referred to the stator side, and we don't use any calculations referred to the rotor side. So everything is referred to the stator side. This is common for all electrical machine books you can find in the market. Okay, so R2 prime is the rotor resistance referred to the stator side. X1 equals X2 prime equals 0.5 ohms. And this is also is going to be most of the time equal. Why? Because actually, how to identify the motor parameters of the induction motor? When we identify the parameters, we assume that the two leakage reactances are equal. So in most of the problems, you will find that X1 and X2 prime are equal values. And Xm is the magnetization reactance is given 30 ohms. So the rotational losses are 1700 watts. So the rotational loss of the machine is 1700 watts, and this is constant value. By the way, all of the time we consider that rotational loss is constant for the induction motor, which means whatever the load, whatever the speed, the rotational loss are going to be the same. Okay. With the rotor terminals short-circuited, find. And then we need to calculate something here. I'd like to stop at this expression here. With the rotor terminal short-circuited. What's the meaning of the rotor terminal short-circuited? We mentioned that we have already here wound rotor type. So for the wound rotor type, the stator windings are like that. I'm sketching just the windings. And we supply this here from the three-phase supply, A, B, and C. And the rotor windings are like that. And if every winding is connected to the slip rings. The question, if we supply the machine like that, will the motor start or rotate? So the answer is no. Why? Because actually it's going to be like a transformer. In order to operate the machine, the concept of the induction motor operation is to have closed path to allow the current to flow, and this is what's called induction, self-induction. So the rotor circuit has to be shorted. So if the rotor is not shorted, the machine is not going to start. So this has to be clear, guys. So short-circuited here means it's just closed in order to allow the motor to start. It doesn't mean there is a short circuit on the motor or there is a fault in the motor, okay? So the first thing is find the starting current when started direct on full volt. Full volt means we are going to apply the supply volt here and see how much starting current we have. We have the motor parameters, so we can start doing our calculations. So let's solve the first part here firstly and go step by step. So this is our equivalent circuit, guys. This is R1, X1, X2 prime, R2 prime divide S and Xm. For the starting, you know S equals 1. So you can have the equation now I input, which is I1 here, equals I2 prime plus Im. So it's written here I1 equals Im plus I2 prime. So Im is nothing but V1 divide JXM plus I2 prime, which is V phase divide this impedance here, which is R1 plus R2 prime divide S plus JX1 plus JX2 prime. And substitute the values now. So at starting, S equals 1. So here we have S equals 1, and we have all the other values here. Take care that we mentioned that this is Y connection machine. So V phase is going to be V line divide root 3, divide J30, which is JXM. The same V line divide root 3, divide R2 prime divide S. So S equals 1 plus 0.25, which is R1 plus J0.5 plus J0.5 JX1 plus X2 prime. So we got this value of current, 250.3 at the angle minus 66.6. So this is the motor starting current. The second thing here is the starting torque. How can we get the starting torque? You can use the current equation, the current value, and you have already the relation of torque. Torque equals P gap divide omega. So you can say P air gap divide omega S equals 3I square R2 prime divide S divide omega S, and again S equals 1 in the starting. So this is our current I2 prime. We need to get I2 prime alone. So I2 prime is this part only. So we just repeated this part here to know the value of I2 prime. So this is I2 prime that we have. When you apply or use the current in this equation, guys, of torque, we use only the absolute value. We don't know the angle, because by the end, the torque is average torque and depends on the RMS value of our current. So it's not a vector. Torque is not a vector here. Torque is just the average value of the torque. So this equation represents the average value, not a vector. So we have to use I RMS. So 3 times I RMS square times R2 prime divide 1, which is S, divide our omega S. So omega S is nothing but pi divide 30 times NS. NS in this case is 1800 RPM. From where we got this one, it's not given. But you know that NR is 1740, and this means the closest NS is going to be 1800. Or you can have 120 times frequency, which is 60 hertz here, divide number of poles, which is 4. So this is also 1800. So we got from here the starting torque. I'm going to write down here or make like boxes around these values, because we need to compare that at normal operating conditions. Sorry, not normal, let's say the loading condition compared to the starting. Okay. So we solve it now, part A. Part B, in full load, we need to get the full load slip. So slip is NS minus NR divide NS. And full load speed is given actually in the problem here. So simply we can calculate the slip. So S equals NS minus NR divide NS. So we can calculate this slip. So the slip here is 0.0333 like that. I'm expecting now he will ask, find the other current and torque. Sorry. Find the other current and torque at this operating condition. So he asked here, find the full load current. So starting with the full load current, so we are gonna do the same equation, okay, but at S equals 0.0333. So the same here, guys, we did the same, but at S that we have, and we got this value of current. Now we need to stop. Let's see, guys, how much current we have at full load compared to the current we draw at starting. Can you see, guys, 44 ampere compared to 250 ampere. So very huge value. Very huge value, 250 compared to 44. It's more than 5 times. And we mentioned that starting current is going to be 5 to 7 times from full load current. And this is what we have here. Okay, so this makes sense according to our theoretical studies or our basics of the induction motor. Okay. A third question here is ratio of starting current to full load current. And this is the one we just said right now. What is the ratio? So just divide 250 over the 44 ampere to get that ratio. So I starting 250 divide 44, it's 5.66 times, which is from 5 to 7 as we just discussed. Then find the full load power factor. And I would like to calculate also the starting power factor, because this is going to give you some like understanding for the power factor values at starting and at steady state. So let's calculate firstly the power factor at starting. So from here, guys, you know that power factor is cosine theta v minus theta I. So we assumed here that v is at a reference at angle 0. So can you see here, volt, we didn't add angle, which means the angle of the volt is 0. So in this case, we can say power factor at starting equals cosine the angle, which is 66.6. If you calculate that, it's going to be 0.397. The type, all the time, the induction motor power factor is lagging. You remember, guys, in the synchronous machine, we had the option to control the motor power factor because there is internal excitation that we can use to control the power factor. But in induction motor, we don't have that. So the power factor of induction motor is constant. It's not controlled. And all the time is going to be lag. Constant, sorry, I mean by constant, it's not controlled. But at starting, it's not going to be different to at full load and different to any other loading conditions. But all the time, the power factor of the induction motor is lagging power factor. It's not possible to be unity or leading power factor. So we got here 0.397. This is very small power factor. Let's see what about the power factor at the full load. So the full load condition here, guys, the angle of the current here is 20 degrees. So cosine 20.4 is 0.936. So this is very nice power factor. So we need to stop at this point. We need to understand. Now, when you buy an induction motor, Which power factor do you care of? The starting power factor or the full load power factor? So starting power factor, guys, is nothing but a transient period. However, the full load is the steady state period, which means transient period can take like few milliseconds. But steady state period of the induction motor, it could be 24/7. The motor can work forever, for instance. So we have class S1, so classes of or duty cycle of the machine. Duty cycle means how long the machine can work per day. So we have what's called class S1. Class S1 is continuous working operation, so it works 24/7. So it's designed to evacuate the thermal heat from the motor, from the windings and core, in order to allow the machine to work forever. So it has a cooling system or maybe self-cooling. It depends on the motor cooling type. That cooling system or the energy or losses will produce heat. So this heat will be evacuated from the machine in order to allow the machine to work safely. Otherwise, if the machine reach to a certain temperature, which may melt the machine windings or affect the core, so this would burn the motor. So we have to evacuate the motor heat from the machine in order to allow the machine to work safely. So we have one of the classes, class S1, this work for 24/7, which means we care about the steady state, not the transient, in terms of the power factor. So power factor is not important for the transients. It's very important for the full load operation or the operating condition because the machine will absorb reactive power during operation. But it will absorb very high reactive power in the transient period, but this is going to be just in very few milliseconds. For sure, it depends on the machine size. If the machine size is larger, so the transient period may be a bit longer, okay? However, compared to the steady state, it's a very small value and can be neglected. So we care more about the steady state power factor, not the transient or the power factor at starting. Okay. The question after is, what is the full load torque? So as we made to calculate the torque at starting, we will do the same also to calculate torque at full load. So full load torque, we have I2, or we can calculate I2 at the full load. So this is I2 at the full load by the same way, guys. So it's nothing but the second part here of the equation. This is I2 prime. So calculating the I2 prime and use it in the equation here. So 3I2 prime squared times R2 prime divide S, and don't forget S equals 0.0333 divide omega S, which is calculated before. So we end up with the full load torque is 176.8. I'd like to compare that with the starting torque. So here we have 176.8 and here we have 186.7. So torque starting is a bit higher compared to our full load torque, and we mentioned that T starting can be from 1 to 1.5. Okay, so this is the full load torque in this case. Now we need to calculate the internal efficiency and motor efficiency at full load. What is the meaning of internal efficiency? So internal efficiency, guys, is referring to the efficiency between the gap power and mechanical power. Why we care about that efficiency? Let me go to the equivalent circuit in order to discuss more about these points. So here is our equivalent circuit. This is R2 prime divide S. We mentioned that, guys, we may neglect the rotor resistance here. So this can be neglected to P0 sometimes. Can we neglect the rotor resistance as well? It's impossible. We cannot neglect the rotor resistance of the induction motor because actually the power is depending on the value of R2. We cannot neglect this power. So you can neglect the copper loss on the stator winding, but the copper loss on the rotor winding cannot be neglected. So from the power flow, guys, you know that if this is P gap after having like some losses before, okay, so this is P gap. We have here copper 2 losses, P copper 2, and the remaining power here will have the P mechanical. So the internal efficiency means P mechanical divide P air gap. So P mechanical divide P air gap is nothing but 1 minus S. And we call this as internal efficiency or ideal efficiency. Why ideal? Because if you neglect all other losses of the machine, you cannot neglect the copper loss of the rotor. So for that, you know that ideal, all of the time, the ideal efficiency of any device should be like 100%. But for the induction motor, the ideal efficiency is 1 minus S. It's impossible to be 1 or 100%. So again, guys, let's go to our question. So the ideal efficiency or the internal efficiency is 1 minus S. So we can calculate 1 minus S. So this is 0.9667. So this is the ideal efficiency or internal efficiency of the machine. But the exact efficiency at full load, we can calculate by means of our power flow right now. So P mechanical minus P rotor. So P mechanical is 1 minus S times P air gap. And we can calculate the P air gap as 3I square R divide S minus P rotational, which is given, divide input power, which is root 3 V line I line power factor. So this is again here 1 minus S times our P air gap. So P air gap is calculated before, okay, minus the rotational loss, which is given 1700, divide root 3 V line I line times the power factor. So this is the efficiency. So the efficiency has to be less than the ideal efficiency for sure. Okay. Last thing, we will end up with this point here in this class, and next class we can continue discussing the remaining parts. We need to calculate the slip at which maximum torque is developed and the maximum torque developed. So this is the direct substitution, guys, in the relation of S maximum and maximum torque. So S maximum here is R2 prime divide R1 square plus X equivalent square. So just direct substitution in order to get the value of S maximum, and then substitute in the T maximum relation, 3V squared divide 2 omega S times R1 plus R1 squared plus X equivalent square. So we have all the parameters, so we can substitute and get the maximum. If you compare, the maximum torque is 438 and the full load torque was 176.8. So it's like 3 times maybe, okay? So, or less than 3 times. So this is the maximum torque number we have in this condition. We still have some questions. Let's finalize these questions quickly. So the slip at motor starting equals, so according to the relation, slip equals ns minus nr divide ns. So at 0 or at starting, 0 speed means slip equals unity. The high operating point slip slip means if S is high, reflects blank motor efficiency. So if S is high, this means the ideal efficiency is 1 minus S. So if S is high, the ideal efficiency is going to be low. So the exact efficiency is going to be lower, which means the high operating slip will be reflecting to lower motor efficiency. The rotor copper losses or loss is a function of stator resistance, rotor resistance, loading condition. Actually, rotor copper loss is I square R, so it depends only on the rotor resistance. It's not depending on a loading condition. Sorry guys, I can say both, not only rotor resistance, because rotor copper loss is I square times R. For sure, my times 3 for 3-phase. So loading condition will affect the operating current as well, correct? So I can say the I is affecting also, so we can select both. But stator resistance, this is incorrect. Okay. Okay. In 3-phase squirrel cage induction motor, rotor conductors are kept open. Rotor conductors, the conductor ends are short-circuited through slip rings. Rotor conductors are short-circuited through end rings. Rotor conductors are connected to the insulation. Actually, kept open means it's not going to work, and squirrel cage has nothing to do outside. There is no connections for the rotor. So this is incorrect. Sorry. So the first one here is incorrect. Rotor conductor ends are short-circuited through slip rings. There is no slip rings. Rotor conductors are short-circuited through end rings. Yes, we have end rings for the squirrel cage. Connected to insulation, it's impossible to be connected to insulation. It's going to be short circuit. So this is the correct answer. At standstill condition, the value of slip is standstill means starting. Motor is still at 0 speed. So at 0 speed, you know slip is unity. The condition of maximum starting torque. This is starting torque. And you know starting torque is S equals 1. The condition for maximum starting torque. Maximum starting torque means I need to move this curve here. And this can be done, guys, by speed control or controlling the machine. So I can do that by controlling the machine. So in order to do that, this means S maximum should be unity. And you know that S maximum equals R2 prime divide X equivalent if we neglect the value of the stator resistance. So if S maximum is obtained at starting, so this means S maximum equals unity. So the condition for that is going to be this is equals 1, so this means R2 prime should be equal to X equivalent. So this R2 prime equals to X total. So this is the correct answer here. In which of the following region induction motor operation is stable? Low slip region, high slip region, any of the two, none of the above. Actually, it's going to be low slip region as we discussed before. 50 hertz Three-phase induction motor has full load speed of 1440 RPM. So this is the full load speed. The number of poles with this machine is 100%. This is going to be 4 poles because this speed is close to 1500 RPM synchronous speed. So this will happen at 40 poles for the 50 hertz machine. Three-phase 50 hertz induction motor has full load speed of 1440 RPM. The full load slip will be 3%, 5%, 4%, 2%. So you need to make calculation. What is 1500 minus 1440 divide 1500? So if you do this calculation, it will be 4%. So the correct answer is 4%. So this is a summary for what we have discussed today, guys. Next class, we will start with the modes of operation of the induction machine. So this is one remaining objective. We will cover it in the next session. Thank you so much, guys, and see you next session.